सो कल का वीडियो से कंटिन्यू करते हैं. सो टुडे वी हैव स्ट्रेट स्ट्रेन कर्व ऑफ अ मेटल. तो यहाँ पर स्ट्रेस और स्ट्रेस वर्सेस स्ट्रेन का कर्व करेंगे. तो व्हाट वी हैव along the y axis we have stress and along the x axis we have strain. Now, so what happens? Last class, just like we have discussed, so if you keep on if you keep on increasing the deforming force, then there will be relation between the stress and strain will be directly proportional by Hooke's law. So you will have, if you see here, this one starting from here, we have got a linear graph in here. This one is linear, so they are directly proportional. That's why it is linear from A to B. The curve is linear. Hooke's law is obeyed. The body regains its shape when the deforming force is removed. तो इस region पे suppose we are giving a deforming force and suddenly we remove that thing. So within this region 0 to A, the body will regain back its original shape. Okay, so from 0 to A it will do that. Now from A to B, so if you see from A to B, the curve is no more linear. It has taken a curve shape like that. So the stress and strain are not proportional. So from A to B they are not proportional, but still the body regains its original dimension. So even after going in that position, the position in which it is not no more linear, the body again regain back to its normal shape. And this point, when it does that, so this point is known as yield point. This this one, yeah, I will just cut this one. So this point B is known as a yield point, and the stress, corresponding stress, means if you so you have the point in here and you draw a perpendicular to the y axis, you will have sigma y in here. So this sigma y is known as the yield strength. So yield strength is the maximum amount of strength which the objects have, through which it regain back to its original shape. तो इसको yield strength कहते हैं. Now what I'm going to do is now increase it further. If the load is increased further, तो load को अगर मैं बढ़ाता हूँ, उसका मतलब deforming force को अगर मैं बढ़ाता हूँ, तब क्या होगा? तो now we'll experience this region B to D region. B to D region we will have if I keep on increasing. Now even for a small increase, even for a small increment of a stress, देखो यहाँ से लेकर यहाँ तक कितना small increment हुआ, the strain increases more. So even for a small increase in stress, the strain increases in more quantity. So here you see if the load is increased further, the stress developed exceeds the yield strength. तो अगर stress yield strength से बढ़ जाता है, if the stress increases beyond the yield strength, the strain increases rapidly even for a small change in the strength. The strain increases rapidly even for a small increase in stress. Even थोड़ा सा भी stress अगर बढ़ेगा तो strain बहुत ज़्यादा होगा, right? तो if the load is removed at C, अब अगर ये point C पे, now if I have this point C and if I remove the load, so we are going from A to B, then B to C. So at the point C, if you now remove the load, deforming force, if you remove the deforming force, then what happens? Then from the point C, it does not regain back to its original shape. Basically the object becomes deformed. So now it comes at this point. So if you remove the deforming force, so the stress becomes zero, but the strain is no more zero. The strain is at this point, and this point is known as permanent set. उसका मतलब permanent damage हो चुका है. Okay, so this point is that in this case, even if the stress is zero, the strain is not zero, so it does not regain to its original dimension. The material is said to have a permanent set. The deformation is said to be plastic deformation. तो वो अपना elasticity, it lost a little bit of elasticity, so it is what? Plastic deformation it is called. The point D on the graph is the ultimate tensile strength. So ये जो point D है, it is known as the ultimate tensile stress. So why ultimate? So you see the difference between point D and point E. So in that portion, what happens to the graph? So from B to D, if you keep on increasing the stress, what happens is that the strain increases very, very rapidly. But from the point D, beyond point D, what happens, if you decrease the stress, if I lower the stress, still the strain increases and it goes to a point in which it breaks. So that point is known as fracture point. तो यहाँ पर the point D on the graph is the ultimate tensile strength of the material. Beyond this point, additional strain is produced even by reduced applied force. अगर मैं applied force, deforming force को थोड़ा सा अगर reduce करता हूँ, तब भी मेरा क्या होगा कि strain बढ़ेगा. And fracture occurs at point E if the ultimate strength and fracture points D and E are close. अगर ये D और E point बहुत close है, अगर पास है ये D and E point, fracture point is very very near. So what we have, that material is said to be brittle. तो उस type of का material को हम लोग brittle कहते हैं. And if they are far apart, अगर तो ये हम लोग कहते हैं brittle. तो if they are far apart, so now if I have the point D as in here, there D and E are far apart, then that type of metals are known as ductile, जिसके बारे में हम लोग बाद में discuss करेंगे. So that was the graph of the stress and strain. Now we have type of modulus of elasticity. We have done type of stress, type of strain. Now we have modulus of elasticity. So basically क्या था modulus of elasticity? So if I have a force per unit area, that's your stress, that is equal to modulus of elasticity E into del L by L. So del L by L, this is for we are giving normal strain in here or normal stress in here. So del L by L इसके लिए आता है क्या है, Young's modulus of elasticity. So for this one, this modulus is known as Young's modulus. तो Young's modulus of elasticity is defined as a ratio of normal stress. अब नॉर्मल स्ट्रेस के बारे में हम लोगों ने ऑलरेडी पढ़ा है. नॉर्मल स्ट्रेस का मतलब क्या है, इट मीन्स टेंसाइल स्ट्रेस और इट इज़ कॉल्ड कॉम्प्रेसिव स्ट्रेस. तो इसको कहते हैं नॉर्मल स्ट्रेस टू द लॉन्गिट्यूडनल स्ट्रेन. ना लॉन्गिट्यूडनल स्ट्रेन का मतलब द लेंथ इंक्रीजेस. तो longitudinal strain means del L by L within the elastic limit and is denoted by Y, Young's modulus. Elastic limit means it does not lose its elastic property or it does not become like a plastic characteristics. Now bulk modulus. So bulk modulus of elasticity, we have studied this one in case of volumetric stress for this thing. तो इसका क्या था, for this one it was B was given by minus P divided by del V by V. This was the formula for volumetric stress. So basically here pressure, यहाँ पर pressure आता है, जैसे कि यहाँ पर force per unit area, ये तो pressure ही है, तो यहाँ पर आएगा P is equal to minus B into del V by V. This was the volumetric stress with volumetric strain. So that's how we get bulk modulus of elasticity. So again within the elastic limit, and ये generally होता कब है, जब we immerse any solid thing inside a liquid. So pressures get applied from every single on the surface of the liquid. From the surface of the liquid, pressure get applied at every single point on the body perpendicularly. Okay, तो अगर यहाँ पर अगर liquid है तो क्या होगा कि अगर मैं बॉडी इमर्स करता हूँ तो लिक्विड से चारों तरफ से परपेंडिकुलरली फोर्स अप्लाइड होगा, तो उसी से आता है वॉल्यूमेट्रिक स्ट्रेस. सो बिकॉज ऑफ दैट फोर्स द वॉल्यूम डिक्रीजेस. सो यू सी, एंड इफ यू टेक दैट ऑब्जेक्ट आउट, द रिस्टोरिंग force act and it tries to regain back to its original shape. So we have the del V by V, that's as the volumetric strain. Now after that we have modulus of rigidity. तो modulus of rigidity कब आता है, when you have the shearing stress और tangential stress जो हम लोग अप्लाई करते हैं. tangential stress मतलब 90 degree to the direction of the strain. तो here what happens is the container we have, it shifts by an angle. So this one is your del x, that's the strain generated, and this length is L. So you have a theta in here, and tan theta was given by del x by L, which we have discussed previously. It is defined as a ratio of the tangential stress to the shearing strain within the elastic limit. So tangential stress to the shearing strain. It is denoted by G. So SI unit of modulus of elasticity is Newton per meter square. For everything, for every one of them, the SI unit is Newton per meter square और पास्कल. बिकॉज वी सी दिस वन कि अगर मैं देखूंगा, चेक करूंगा, यहाँ पर देखो जैसे फोर्स पर यूनिट एरिया, उसका मतलब तो प्रेशर है, और ये डेल एल बाई एल, डेल एल बाई एल जो है ये तो डायमेंशनलेस है, इसका कोई डायमेंशन ही नहीं है. यहाँ पर भी वॉल्यूमेट्रिक सिस्टम ये डेल वी बाई वी है, इसमें भी कोई डायमेंशन नहीं है. तो ये जो बल्क मॉड्यूलस है इसका डायमेंशन प्रेशर का डायमेंशन जैसा होगा, तो दैट इज न्यूटन पर मीटर स्क्वायर और पास्कल. तो विल डिस्कस ईच वन ऑफ देम. तो यंग्स मॉड्यूलस क्या होता है कि y इज गिवन बाय नॉर्मल स्ट्रेस डिवाइड बाय लॉन्गिट्यूडनल स्ट्रेन. जैसे कि यहाँ पर मैं दिखा रहा था कि F बाई ए, सो आई विल राइट हियर F बाई ए इज इक्वल टू y डेल एल बाई एल. तो यहाँ से मैं क्या करूँगा, y का वैल्यू क्या हो जाएगा, y विल बी इक्वल टू F बाई ए डिवाइड बाई डेल एल बाई एल. सो दैट्स हाउ वी गेट द यंग्स मॉड्यूलस. नाउ फॉर मेटल्स यंग्स मॉड्यूलाई आर लार्ज. तो मेटल के लिए यंग्स मॉड्यूलस बहुत ज़्यादा होता है. देयरफॉर these materials require a large force to produce a small change in length. तो किसी भी मेटल्स के जनरली क्या होता है कि यंग्स मॉड्यूलस बहुत ज़्यादा होता है. तो सिंस द यंग्स मॉड्यूलस इज वेरी वेरी बिग, सो व्हाट हैपेंस इज दैट तो मेटल्स नीड अ वेरी लार्ज फोर्स टू प्रोड्यूस अ स्मॉल चेंज इन लेंथ. तो इसको समझने के लिए एक काम करते हैं हम लोग, F निकालते हैं. तो F इज इक्वल टू व्हाट यू गेट इज, यू सी F बाई ए इज वाई डेल एल बाई एल इंटू ए. तो ए को मैं उस तरफ लेके जाऊंगा, तो वाई ए डेल एल बाई एल. ओके, ना फॉर द मोमेंट व्हाट आई एम गोना डू इज, ये वाई ए बाई एल इसको हम लोग एक कांस्टेंट ले लेते हैं. ए बाई एल को एक कांस्टेंट ले लेते हैं. सपोज ए बाई एल का वैल्यू 1 है, तो इसको हम लोग वाई डेल एल ले लेते हैं. आई एम एक्सप्रेसिंग दिस वन एज वाई डेल एल. ओके, नाउ think of that y value. Let us take the y value as 1000. So for the moment we are taking two equations. I'm taking y value as 1000 and we are taking force where y value is 10. यंग्स मॉड्यूलस एक के लिए 1000 है और 1000 पास्कल है, और एक के लिए 10 पास्कल है. राइट, नाउ वी वांट टू इंट्रोड्यूस चेंज इन लेंथ ऑफ व्हाट शुड आई से 1 सेंटीमीटर का हम लोग चेंज इन लेंथ चाहते हैं. तो अगर 1 सेंटीमीटर का अगर हम लोग चेंज इन लेंथ चाहेंगे तो फोर्स विल बी इक्वल टू व्हाट, फॉर दिस मटेरियल विच हैज़ 1000 यंग्स मॉड्यूलस, फॉर दिस वन वी नीड 1000 इंटू 1, दैट इज 1000 न्यूटन का मुझे फोर्स चाहिए टू हैव एन 1 सेंटीमीटर ऑफ डिफॉर्मेशन फॉर अ क्वांटिटी विच हैज़ 1000 यंग्स मॉड्यूलस वैल्यू एज 1000. बट इफ आई हैव फॉर दिस वन हुज यंग्स मॉड्यूलस इज 10, तो इसके लिए मुझे कितना न्यूटन फोर्स चाहिए. तो टू इंट्रोड्यूस अ 1 सेंटीमीटर डिफॉर्मेशन आई नीड, और 1 मीटर डिफॉर्मेशन आई नीड अ 10 न्यूटन फोर्स इन हियर. यहाँ पर कितना चाहिए था, यहाँ पर जैसे 1 मीटर डिफॉर्मेशन के लिए 1000 न्यूटन चाहिए है, तो यहाँ पर 1 मीटर डिफॉर्मेशन के लिए 10 न्यूटन फोर्स चाहिए. ओके, सो यू सी द डिफरेंस. सो द हायर द यंग्स मॉड्यूलस, greater the force we need for the equal amount of deformation. So now from here we'll come across something which we have learned about spring. तो spring में restoring force क्या था? So it was given by minus kx. This was the restoring force of the spring. Now for the moment let us forget the minus sign. So let us have this one, force is equal to kx, where kx was the length through which the spring has been डिफॉर्म्ड. वाई स्प्रिंग. तो बेसिकली क्या होता है, x का वैल्यू क्या है कि अगर जितना ज़्यादा अगर मैं ये फॉर फोर्स अप्लाई करता हूँ, इफ़ आई अप्लाई अ फोर्स इन हियर एंड यू सी दैट द स्ट्रिंग स्ट्रेचेस, तो द अमाउंट टू विच द स्ट्रिंग स्ट्रेच दैट गिव्स यू द वैल्यू ऑफ x, एंड दैट इज नथिंग बट द डिफॉर्मेशन इन द स्प्रिंग. ओके, तो बेसिकली ये जो x है ये डेल एल है, इट्स नथिंग बट del L. So from here what we see, F by A, हम लोग यंग्स मॉड्यूलस से क्या फॉर्मूला पढ़ा है? F by A is equal to Y del L by L, right? So now here let us find out F. So F comes out to be what? F is YA by L into del L, sorry, del L. Now if I compare this X corresponds, this X is small, the change in the spring length, and this del X is also the change in the rod which we experience. So what remains is, you see here the value of K, and here it's YA by L. So from here we get the spring constant, that is X is equal to YA by L. So Y is the Young's modulus, A is the cross-sectional area, and small L, actually this won't be small l, it has to be capital L in there. So capital L, that is the length of the spring or wire we have. So this is how we get the spring constant, and that is also known as the force constant. Then we have shear modulus. So shear modulus is given by G, and that is shearing stress divided by the shearing strain. So this one is also known as tangential सरफेस के अक्रॉस टेंजेंशियल फोर्स अप्लाई करके शेयरिंग स्ट्रेस आता है, जनरेट होता है बॉडी के अंदर टू काउंटर दैट फोर्स. तो इट इज़ F डिवाइड बाई A डिवाइड बाई del x by L, and I already told you del x is written as theta, which we have already discussed this one before. So del x by L ये होता है tan theta, and theta is very very small, so that is equal to theta. So this is your shearing strain. तो shear modulus is generally less than Young's modulus. तो shear modulus क्या होता है? ये Young's modulus से छोटा होता है. तो for liquids modulus of rigidity is 0, because in case of liquids we cannot have shearing stress. Okay, it is only applicable for solids. So Young's modulus and modulus of rigidity are possessed by solid materials only. Then we have bulk modulus. अब ये bulk modulus क्या है? Which we have already discussed. It comes from volumetric stress divided by volumetric strain. तो volumetric stress we have, and that formula is given by minus P divided by del V by V. So if you put any object inside some liquid, so there will be a pressure applied to that surface of the body by the liquid perpendicularly to every single point on the surface of the body. Okay, now if you take that liquid out, what happens, if you take the solid out, what happens is that the solid generates some restoring force to get back to its original shape. तो ये प्रेशर के वजह से वॉल्यूम चेंज होगा. सो दैट्स हाउ वी गेट del V by V, that's the volumetric strain you have, and it actually came for what reason? Because of the pressure. Now it acts in the why there is a negative sign. So the negative sign indicates the fact that with an increasing pressure, जितना pressure बढ़ेगा, a decrease in volume occurs. The more the pressure from outside, from the liquid, there will be a further decrease in the volume. That is why it is negative. That is, if P is positive, अगर P का वैल्यू पॉजिटिव है, then del V नेगेटिव होगा. ऑब्वियस सी बात है कि ज़्यादा प्रेशर होने से V2 जो वॉल्यूम 2 होगा, वो वॉल्यूम 1 इनिशियल वॉल्यूम से कम होगा. तो इसीलिए V2 माइनस V1 माइनस del V, so it will be negative. Thus for a system in equilibrium the value of bulk modulus is always positive. लेकिन किसी भी सिस्टम, कोई सिस्टम अगर इक्विलिब्रियम में है, बल्क मॉड्यूलस का वैल्यू पॉजिटिव होगा. ओके, बिकॉज व्हाट हैपेंस इज दैट बल्क मॉड्यूलस यहाँ पर ये चेंज की वजह से हो रहा है कि del V by V, बट अगर कोई सिस्टम इक्विलिब्रियम में है तो उसका बल्क मॉड्यूलस नेगेटिव नहीं होगा, पॉजिटिव रहेगा. Now the bulk moduli for solids are much larger than for liquids. So bulk moduli for solids are much larger than liquids, which are again much larger than bulk modulus for gases. Okay, तो gases का bulk moduli सबसे कम होता है. उसके बाद so we have here कि bulk modulus for solids is greater than bulk modulus of liquids, and that is greater than bulk modulus of gas. So this is what we learn about bulk modulus. Now from the bulk modulus we have another thing which we come across is compressibility. Now किसी भी चीज़ को compress करना, we are compressing something basically means we are applying force in every single direction like this. Now if I have a rod like this, compression का मतलब क्या है कि मैं force, जैसे कि दो तरह का फोर्स होता है, एक होता है टेंसाइल फोर्स, तो इससे इसका लेंथ बढ़ेगा, एंड द अदर टाइप ऑफ फोर्स इज कंप्रेसिव स्ट्रेस विच वी हैव, तो वी ट्राई टू रिड्यूस द length of that thing. The reciprocal of bulk modulus is called compressibility and is denoted by K. So 1 by B, this is your compressibility and is denoted by K. It is defined as a fractional change in volume per unit increase in pressure. तो जैसे कि B का वैल्यू कितना क्या देखा था मैंने, -P डिवाइड बाई डेल V बाई V. तो यहाँ पर compressibility that is K, that will be equal to what, इसका और रेसिप्रोकल मतलब डेल V बाई V डिवाइड बाई, अच्छा माइनस आएगा P. दैट्स योर कंप्रेसिबिलिटी. ओके, एंड हियर वी हैव दिस डेल P. डेल P बेसिकली मीन्स व्हाट, चेंज इन प्रेशर. तो ऑब्वियस सी बात है, चेंज इन प्रेशर तभी आता है जब ज़्यादा मैं कंप्रेस करूँगा तो प्रेशर ज़्यादा बढ़ेगा. तो चेंज इन प्रेशर हियर वी हैव टू कंसिडर. सो दिस वन ऑल्सो यू कैन राइट डेल P इन हियर. चेंज इन प्रेशर के वजह से जितना ज़्यादा हम लोग, एक्चुअली इट्स फ्रॉम द फ्लूइड्स ओनली, द मोर यू इंसर्ट द सॉलिड बियॉन्ड द हाइट, ये रो एच जी, इसको जितना हम लोग अंदर कंटेनर के अंदर दबाएंगे उतना तुम्हारा प्रेशर बढ़ेगा. ओके, एंड द ग्रेटर द प्रेशर द वॉल्यूम also there will be a change in volume. So like this way you will have the bulk modulus. So that's why they have used del P in there. They are considering the change in pressure. Thus solids are less compressible whereas gases are most compressible. So just like here what we have studied that कि solids का bulk modulus सबसे ज़्यादा होता है, तो compressibility के लिए क्या होगा कि K of S will be less than K of L will be less than K of G. The compressibility of the gases will be more than liquid, and then it will be further more than solids. Okay, so gases are about million times more compressible than solids. Gases have large compressibilities which vary with pressure and temperature. तो gases का जो compressibility है वो pressure और temperature के साथ vary करेगा. तो obviously we have seen in here कि pressure के साथ vary कर रहा है because it's inversely proportional to the change in pressure. So the incompressibility of solids is primarily due to the tight coupling between the neighboring atoms. तो the reason is that कि solids को हम लोग ज़्यादा compress नहीं कर सकते कि इसका compressibility बहुत low है. The reason is because of the tight coupling between the neighboring atoms. तो एक atom के दूसरे atom के साथ tight coupling है, interatomic forces से they are tightly coupled. So that's why यहाँ पर compressibility बहुत कम है. The molecules in liquid are also bound with with their neighbors, but not as strong as solids. But still, it is strong as compared to gases. Gases में they are not that much of strong, so इसीलिए compressibility बहुत ज़्यादा है gases का. Next thing is Poisson's ratio. अब Poisson's ratio कैसे आता है? Now, when I think of a rod, जब मैं एक rod के बारे में सोचूंगा, and we are giving a tensile we are applying a force like this, so tensile stress will act, and what happens is that कि इसका जो length है ये बढ़ेगा ऐसे करके, तो the length of the rod increases and it increases about del L time. But due to this increase in length, the area the cross sectional area will not be same. What happens here, the cross sectional area decreases. यहाँ पर क्या होता है कि जो क्रॉस सेक्शनल एरिया है वो छोटा हो जाएगा. तो हियर देर इज ऑल्सो अ स्लाइट रिडक्शन, देर इज अ स्लाइट रिडक्शन इन द क्रॉस सेक्शन ऑफ द वायर. द स्ट्रेन परपेंडिकुलर टू द अप्लाइड फोर्स इज कॉल्ड द लैटरल स्ट्रेन. इसको लैटरल स्ट्रेन कहा जाता है कि यहाँ पर क्या हो रहा है, डिक्रीज हो रहा है. एंड व्हाट यू सी इज दैट द लैटरल स्ट्रेन वी हैव इज परपेंडिकुलर टू द फोर्स अप्लाइड. तो द स्ट्रेन परपेंडिकुलर टू द अप्लाइड फोर्स से परपेंडिकुलर जो स्ट्रेन हो रहा है, इट इज नोन एज द लैटरल स्ट्रेन. तो साइमन पॉइसन pointed out that within the elastic limit lateral strain is directly proportional to longitudinal strain. तो यहाँ पर जो lateral strain है उसको हम लोग del D लिखते हैं because diameter reduce हो रहा है basically यहाँ पर, तो del D is directly proportional to del L. So Simon Poisson, he found out that thing, so that's why its name is Poisson's ratio. So del D is directly proportional to del L. The ratio of lateral strain to the longitudinal strain in a stretched wire is called Poisson ratio. तो lateral strain divided by longitudinal strain is your Poisson ratio. उसका मतलब del D by D divided by del L by L. तो ये है तुम्हारा Poisson ratio. Okay. So its value depends only on nature of material. तो इसका जो value है इसका हमेशा नेचर ऑफ मटेरियल के ऊपर डिपेंड करता है. नेचर ऑफ मटेरियल के ऊपर डिपेंड करता है. तो लैटरल स्ट्रेन इज योर डेल डी बाई डी, लैटरल लॉन्गिट्यूडनल स्ट्रेन इज योर डेल एल बाई एल. तो पॉइसन रेशियो इज डेल डी बाई डी इंटू डेल एल बाई डेल एल. तो इसको बस इसको मल्टीप्लिकेशन कर दिया, डेल डी बाई डी इंटू एल ऊपर जाएगा और डेल एल नीचे रहेगा. सो एंड अगेन इट हैज़ नो डायमेंशंस बिकॉज यू सी all the meters get cancelled. Now we have elastic potential energy in a stretched wire. तो एक stretched wire पे कितना potential energy generate होता है. So when a wire is put under tensile stress we all know it is like this. तो किसी भी wire को अगर मैं tensile stress देता हूँ तो क्या होगा कि work is done against the interatomic forces. So the interatomic forces, they are trying to keep the solids together, right? So when we apply a tensile stress, so work is done against the interatomic forces. This work is stored in the wire in the form of elastic potential energy. तो ये जो work है, जो हम लोग work क्या होता है? It is force into displacement. So the amount of force, the tensile stress which we are generating, which is acting against the interatomic forces, so it is stored in the form of elastic potential energy. तो उसी को हम लोग निकालने जाएंगे कि when a wire of original length L, जब एक वायर का original length L होता है and the area of cross section is A, is subjected to a deforming force. तो उसको हम लोग क्या कर रहे हैं, एक deforming force अप्लाई कर रहे हैं, and that to how much amount, that to say about F. Let the length of the wire be elongated by L. तो यहाँ पर वो जो this L is nothing but the deformation. So force, we already studied that force per unit area is equal to Y, because we are talking about wire. So there will be longitudinal stress and strain in here. So Y L by L. तो बेसिकली यहाँ पर del L जो था उसको हम लोग small l से रिप्रेजेंट कर रहे हैं. तो हम लोग ने क्या पढ़ा कि force into displacement is work done, right? So we are trying to find out the work done, and that amount of work done is equal to the elastic potential energy. So from here we are trying to find the force. The force is equal to Y A small l by L. So this is the amount of force required for a deformation of L. Okay. So now what we are going to do is this deformation in here. Let me see this one. So if I have a rod like this of length L, okay. Now when we are stretching, when we are applying the force, the deformation directly doesn't go to the length of small l. So it slowly it goes to that deformation. So it means what? If I have the deformation in here as small l, so I will break this deformation into very small parts, and this smaller amount is known as del L. So del L like this, where there are infinite. So basically there are infinite small amount of deformations. We have a del L amount, and those total gives us the L, small l amount of deformations. Okay. So now the work done we have is dW. It is given by F into dl. Okay, that is the work done generated for a small amount of dl amount of deformation, but this deformation is total deformation is L. Okay, so from here we have 0. and this is the total amount of deformation L. So this work done we need to find is from 0 to L. And this dl signifies what? This dl signifies for a very very small amount of deformation. Okay, so what we need to do is we need to add up all those small amount of deformations. It means we need to add up all the infinite amount of deformations. So in order to add infinite amount of deformations, we need to do integration. And integration from where to where? We need to integrate starting from 0. So we're going to start from 0 and to L, that is the largest deformation, that is the maximum deformation which we can have if we apply the force F. Okay, and that is equal to the total work done. So this is your total work done we have. So from here if I integrate, so first we'll put the value of L in here, F in here. So F is Fya small l by capital L into dl, and this L is small l. Okay, so this one is small l, this one is small l, but this thing is a capital L. So if you integrate this one, if you look at here, we do integration. So in integration, just like differentiation, what we do is we take out all the constants we have. So here, what are the constants in here? So Ya capital L, these are the constants we have, and we are integrating with respect to L. So the variable of integration is L. So 0 small l, so L dl. So this is my integration, and as we know, the integration of L is L square by 2. So Ya divided by L into L square by 2, and we are doing from L to 0. Okay, always remember this one. So if I integrate x to the power n dx, so in differentiation what happens? The power, the degree decreases, right? X to the power n, if you differentiate this one, it is n x to the power n minus 1. Okay, so that is the differentiation, but integration is the opposite. It is the reverse process of differentiation. So in here the power of x increases, so here it will be x to the power n plus 1 divided by n plus 1. Remember this one. Okay, x to the, and another thing, here we multiply n and here we divide by the power. Okay, so n plus 1 divided by n plus 1. So that's why we get here the small l has the power of 1. So if you integrate this one, it will be L square by 2. Now this small l is the upper limit, this one is a lower limit. So if I put the upper limit and lower limit, so we'll get the expression as into L square by 2. Okay, so that's how we get the expression. So in this page also we have done that thing. So here the work done dW is given by F into dl, or YAL dl. Therefore the amount of work done is increasing the length of the wire from L to L plus L. तो यहाँ पर ये ओरिजिनल लेंथ L है, तो अभी मैं उस लेंथ को इंक्रीज कर रहा हूँ L प्लस L करके, एंड दैट इज फ्रॉम L इज इक्वल टू 0 टू L इज इक्वल टू L. यहाँ पर मैंने किया था कि L इज इक्वल टू 0 से लेकर L इज इक्वल टू L तक इलोंगेट किया. तो उसको करने के लिए हम लोग क्या किया, हम लोगों ने इंटीग्रेट किया. वी हैव डन द इंटीग्रेशन फ्रॉम 0 टू L YAL L DL. तो बेसिकली ये F DL है, तो F की जगह पे वैल्यू पुट कर दिया, एंड वी गॉट this value, right? Now if you look carefully, so we can express this one in this form. So I'm going to write this one as half y into, यहाँ पर ऊपर नीचे एक L मल्टीप्लाई किया, तो कैपिटल L मल्टीप्लाई किया, क्योंकि एक ही कैपिटल L था तो उसको L स्क्वायर कर दिया. तो वी गोना हैव दिस वन एज, वेट अ सेकेंड, सो L स्क्वायर इंटू A कैपिटल L. तो कैपिटल L से ऊपर नीचे मल्टीप्लाई किया, तो यू गेट अ कैपिटल L स्क्वायर. द रीजन ऑफ मल्टीप्लाइंग दिस वन इज because you see small l is the deformation and capital L is the original length. तो change in dimension divided by original dimension, that gives you, ये किसका value है? This is the value of the strain. Small l by L is the strain, right? And this one is the volume. ये तो volume है. तो I can write this expression as half into Young's modulus, that is y. This y is the Young's modulus, into strain square. Small l by L is the strain, so strain square into volume. Okay, so that's what we have, half into Young's modulus into strain square into volume. Now you will be asking, sir, from where we got this thing? So one thing we know, that stress is equal to y into strain, right? Stress is equal to y into strain. So here you see the expression, so Young's modulus into one of, I have strain square, so one of the strain I multiplied with Young's modulus, I change it into stress. So half into stress into strain into the volume gives you the elastic potential energy. Now sometimes the question asks कि express the elastic potential energy in terms of as a product of stress and strain. तो उसके लिए हम लोग क्या करेंगे, the work is stored in the wire in the form of elastic potential energy. तो ये एक्चुअली हम लोग को जो मिला ये कैपिटल U का वैल्यू मिला. Therefore the elastic potential energy per unit volume of wire. अब यहाँ पर देखो पर यूनिट वॉल्यूम बोला है, तो जब मैं पर यूनिट वॉल्यूम बोलूँगा उसका मतलब क्या, वॉल्यूम मेरा 1 है, तो वॉल्यूम 1 अगर हुआ तो स्मॉल यू इलास्टिक पोटेंशियल एनर्जी पर यूनिट वॉल्यूम विल बी गिवन बाय हाफ इनटू, ये सिग्मा का मतलब क्या है, स्ट्रेस, और दिस वन मीन्स स्ट्रेन, and volume is 1, so we don't need to write the volume. So this is how we can express the elastic potential energy in terms of stress and strain, or maybe the product of stress and strain. Okay, now there are some important terms which you must remember, that is elastomers. Now elastomers are the materials for which strain produced is much larger than the stress applied. तो कम स्ट्रेस में बहुत ज़्यादा स्ट्रेन प्रोड्यूस होगा विद इन द लिमिट ऑफ इलास्टिसिटी आर कॉल्ड इलास्टोमर्स. तो इलास्टिसिटी के लिमिट में कम स्ट्रेस में बहुत ज़्यादा स्ट्रेन जनरेट होगा. तो फॉर देम द ग्राफ ऑफ स्ट्रेस वर्सेस स्ट्रेन, तो इफ़ यू हैव स्ट्रेस इन हियर एंड इफ़ यू हैव स्ट्रेन इन हियर, द ग्राफ विल बी like this. For a small amount of stress you have higher amount of strain. You see, if you look at this region, यहाँ पर देखो कि कम स्ट्रेस दिया लेकिन हाउ मच इज द इलोंगेशन, तो इट्स बिगर, राइट. सो दिस इज हाउ वी गेट इलास्टोमर्स. नाउ द एग्जांपल इज इलास्टिक टिश्यू ऑफ aorta, then rubber, then large vessels carrying blood from heart, and elastomers have no plastic range. तो इसका कोई plastic range नहीं होता है. तो basically जैसे कि we have the deformation for what should I say, yield strength for the metals, तो इसका कोई plastic range नहीं होता कि ये does not, it always have the elasticity in them. Now ductile materials. The ductile materials is what? The materials which show large plastic range beyond elastic limits are called ductile materials. कि large plastic range beyond elastic limits. तो जैसे कि हम लोगों ने देखा था कि B से लेकर D तक, तो if you look at here, if you go graph from B to D, if the gap between D and E, so you see if the gap between D and E is very very small, तो उसका मतलब क्या है, ये जो plastic range है, this is known as the plastic range. So the plastic range is very very small, then that one is brittle, and if the plastic range is very very big, then that one is known as ductile. So the definition which we have here is कि plastic range मतलब कि ब्रेकिंग पॉइंट के पहले जो रेंज होता है. तो डक्टाइल मेटेरियल्स में क्या होता है कि लार्ज प्लास्टिक रेंज बियॉन्ड इलास्टिक लिमिट्स, तो इलास्टिक लिमिट्स के बाद लार्ज प्लास्टिक रेंज होता है, आर कॉल्ड डक्टाइल मटेरियल्स. तो एग्जांपल क्या है, कॉपर, सिल्वर, आयरन, एल्यूमिनियम. तो डक्टाइल मटेरियल्स आर यूज्ड फॉर मेकिंग स्प्रिंग्स एंड शीट्स. ब्रिटल मटेरियल्स, द मटेरियल्स विच शो वेरी स्मॉल प्लास्टिक रेंज, तो इसके लिए बहुत स्मॉल प्लास्टिक रेंज होता है. उसका मतलब इलास्टिसिटी अगर इलास्टिक लिमिट्स क्रॉस कर गया तो वो बहुत जल्दी ब्रेक हो जाएगा. ओके, सो आर कॉल्ड ब्रिटल मटेरियल्स. एग्जांपल ग्लास, कास्ट आयरन. ओके, नाउ malleability. Malleability is when a solid is compressed, a stage is reached beyond which it cannot regain its original shape after deforming force is removed. तो एक स्टेज रीच होता है जब डिफॉर्मिंग फोर्स, if we remove the deforming force, then it cannot regain its original shape. So there we have studied, there was a point C, that is the yield point. So yield point was a point beyond which if you go, then the original shape cannot be regained. So that's the same thing in here. When a solid is compressed, a stage is reached beyond which it cannot regain its original shape after deforming force is removed. This quantity is called malleability of the solid substance. So this is, we have a chapter.